I'm just waiting for NASA people to show up.
Let's wait. Let's wait.
Just a few more minutes so that they can.
Yeah, anyway. It's important to get NASA people sign in, because after all, it's their money.
Right, it's their money, and we're recording this for. I think any minute now we will see them. So Louis, how is life in Hong Kong now? Is it good?
I grew up in Hong Kong. I guess wherever you grow up, you have some habit and some particular food you like, such a habit, So a lot of things I couldn't get in US is easy to get in Hong Kong. I guess the same thing in Armenia.
Okay, so maybe we get started because Kevin White joined from the advisory board. So we're waiting for Irene. Irene will join, I think, any minute now. Sometimes she's running from another meeting. So today I want to welcome everyone, and we have Louis Sharp presenting today with his student actually doing the presentation, because Luisha is in Hong Kong with 19 hours, with 13, 15 hours of time difference. It's 1 a.m. most likely there. So Ayoosh, get started. Thank you very much. Hi, Kevin. Hi, Kevin. So we're talking today about robust perception, simplex for robust perception. And it's very exciting. We have co-authored the paper with Ayoosh. So Ayoosh, get started. So Kevin Wise is the chair of our advisory board. He's here, I guess.
Oh, okay.
Right.
All right. So, okay. So I will give some introduction, and then I will pass on Ayoosh, and Ayoosh will pass on Simon. Okay. So if you look at the big picture, what we are focused is safety. So the model is that we envision the air vehicle can do both flying and ground. And in fact, that you look at Bosch, they make a prototype. I think that for air taxi, building all the landing pads near everybody's house is unrealistic and too expensive in big cities where the air flying taxis need. So our context is safe air plus ground vehicle flying taxis without landing pad. And there are three key components. One is the verifiable safe collision avoidance using physics model, supervised machine learning based vision. The second component is robust or statistically reliable traffic sight recognition against noises and attacks. The third is the safety-driven integration of safe perception, which is perception simplex, the focus on that's a highlight of today's presentation, and safe control basically is L1 simplex, which is existing work between Nana's group and my group. So we want to put it together in a seamless architecture to achieve the safety. So, and then we name it a synergistic simplex architecture. And Ayoosh has made a big contribution, and he will explain what does that mean. All right. Okay. So our approach is extend our research on autonomous ground vehicle to flying taxi. Can you flip the slide? Okay. So the guiding principles are number one, for safety critical requirements, such as obstacle detection in air and on land, we shall have explainable and verifiable analytical model for the system behavior. Actually, that employs AI. All right. So remains explainable and verifiable and using AI. This leads to C6 model supervised machine vision for obstacle detection. Then it said, for example, we will allow the air vehicle landing on a parking lot, which has moving cars, or even learning on the street. Let's say it's not too congested. You think about like bypassing a car. All right. So the control part is also a challenge, and we were counting on NASA, NIRA's team, and then we actually need to work closer. So we are focused is the perception part. For mission critical requirements, such as traffic sign recognition and classification, in spite of noise and attacks, we are integrating robust multi-sensor fusion technologies with machine classification and recognition. So essentially, one guiding principle, say the sensor fusion is a well-established technology in aviation. Now it requires sort of analytic redundant sensors, such as GPS or inertial navigation systems. They have independent frame mode, so such that they won't fail together. So when we replace the sensors by different features from machine learning, for example, the traffic size, shape, color, symbol, and text, they plays the role of sensors. However, in the current generation of the feature recognition, those software, those features, the classification era of features are correlated. You will hear from Simon. That means if somebody attack a color, somehow the probability of classify the shape, say, is the probability of traffic size should be octagon, for example. But if you alter the color, somehow the machine probability, the classification probability for the shape, the octagon, will also drop. That means if an attacker attack one attribute, you can potentially, or in probability, not negligible probability, bring down all attribute. So you mix the composition invalid. So we are working on that. And the first step, actually, Simon have developed evaluation benchmark. So keep everybody honest, whether or not how much things we can tolerate. And the second step, I think, is well in the way, but we haven't get any solid result yet, is to make sure that if we say, what's the probability of the shape? It's octagon. I will give you a number, let's say 90%. Then 90% will not depending on the color change or the lightening condition or what you written on the side or the graffitis. Okay, so these are the two things. So now I pass on to Ayoosh.
Hello, everyone. My name is Ayoosh. So today I'm presenting our work on perception simplex and how we plan to evolve it into something called synergistic simplex. So the current status of this work is we started this work with ground vehicles, and we have created a verifiable fail-safe system for ground vehicles when there are obstacle existence detection faults or false negatives. We have ongoing work on upgrading this to a verifiable fail-safe, but also best effort fail operational system. We have validated our prior work using real-world datasets, which is Waymo's open dataset, and software-in-the-loop simulation using photorealistic simulators called LGSphere, and Baidu's Apollo as our target mission system. We have also ongoing efforts to validate our current system on a real vehicle, a real street legal vehicle, which exists at UIUC. With this group, we are excited to adapt our solution onto air taxis. So going from ground vehicles to vehicles that can transform into air vehicles. We plan to evaluate these adaptations using the photorealistic air vehicle simulator that Professor Petros and Hyunjin Yoon presented in this seminar. And we also want to use their integration of NASA generalized urban air mobility vehicle when it's available. These are the references for the works that have been completed. One of them is under review. So repeating from what Professor Shah said, summarizing it quickly, we consider a generalized air and ground vehicle, which is able to transform between the two. So there is robust perception requirement to be able to integrate into existing traffic. Vertical takeoff and landing vehicles are a subset of this. So of course, whatever solutions we propose for our generalized vehicle would also apply there. we want this vehicle to be able to operate in fully cluttered environments, and hence perception is a big challenge. Other challenges include just the physical design of the system, policy, infrastructure, control, planning, but our focus remains on perception. More than that, there is perception requirements to fulfill the mission of the system, and while there are perception requirements to maintain safety, my focus is on safety.
Ayoosh, there is a question in the chat. Could you maybe same time, Kevin Weiss is asking a question. Do you think it's solved for ground vehicles or?
So I think it is partially solved for ground vehicles. And that is why we are trying to adapt it to, validate it on a real vehicle to have complete certainty that we have solved the ground vehicle issues completely. Does that answer your question?
Yeah, if you think about in a lot of those movies, the flying car. We want to make the flying car into a reality.
Is it? Do you want me to ask questions like real time, or I thought?
Yeah, real time, Kevin. This is discussion. These are informal meetings. Yeah, ask
okay.
real time.
So your opening, your opening chart where you say, okay, we've done this work in ground vehicle detection, but we've had recent experience with autonomous docking with the space station, and when we have Earth in background, there's some real challenges yet still. And another application that we've been doing is aerial refueling, where we have the KC-46 tanker autonomous vision system trying to control the boom to offload fuel into receiving aircraft, and being able to train the software for detecting these things. I don't consider it to be a solved problem. That's what I was kind of wondering, if you're claiming this solved, or if you're just going to take this approach and then try to apply it to the flying car. Okay, over.
So actually, we are not claiming we have solved a problem. We believe it's a solvable problem.
And that we have identified a very promising approach, which, based on our initial results, seems like the right path to take to solving this problem completely.
Okay, very good. I didn't mean to slow you up this much. That's why I put it in chat, just because okay.
Yeah, we understand this is a very challenging problem.
Yeah.
But that's precisely what we want to work on.
Yeah.
If it's not challenging, we are not interested.
Very good.
In fact, I'll point out the residual challenges that we have and how our future approaches try to address them.
Okay, now we are looking at the perception part. Then there's a control part. Probably we need to work with Nara's team and probably present the future and the integration.
All right, so deep learning has enabled some beautiful capabilities that are crucial for modern complex cyber-physical systems like autonomous ground and air vehicles. Unfortunately, these capabilities also come with vast safety challenges, as has been exemplified by real-world collisions, malicious attacks. So there are two major approaches to solving these problems. One is prevention of faults. People have tried and are developing extensive methods for testing these solutions. Unfortunately, as prior works and a lot of analysis on ground vehicles have shown us, we will never test our way out of this problem. So what we need is design for safety. And Professor Boley's work is a great step forward into creating these robust machine learning solutions. And Simon will present his solution later in this talk, which also addresses the same. My approach to this is fault tolerance. You may be aware of prior simplex designs in control systems. Similar to that, we protect a mission layer, which is a complete mission capable system, which provides high confidence guarantees, but these are not verifiable guarantees. But we protect faults in such a system by using a safety layer, which is fully verifiable for its behavior. This, of course, adapts from the previous simplex design, but it is different in some key characteristics. First, unlike prior simplex design, this architecture cannot do everything that the mission layer system does. because the safety layer uses only verifiable solutions and DNN are not a part of that. And as we noted earlier, there are some capabilities that are not doable today without the use of deep learning solutions. Since we have this gap in capabilities of the safety layer system, we also want to be able to utilize the machine learning capabilities without invalidating the safety guarantees that we are trying to provide. And finally, for any runtime monitoring system, we want to minimize the performance loss of adding that system. So the very first step in this procedure is selecting what faults we want to address. To that end, we started with a survey of all the fatal collisions that have involved ground vehicles and some level of autonomous control of the vehicle. Till date, there have been 20 such fatal collisions where autonomy may not be directly responsible, but it was involved. 4 of them have been fully analyzed by NTSB and public reports are available. All 4 of them involved obstacle existence detection fault, where some obstacle in the vehicle's environment was not detected or responded to. Other 16 cases, although we do not have complete information, but based on public reporting and how the crashes happened, we suspect the same fault to exist, which means that this is clearly the first fault we should be focusing on. And all these collisions could potentially be avoided if we have a complete solution to this. So the next step is, what do we mean by obstacle existence detection? What is the minimum we need to do to identify the existence of an obstacle enough so that we can avoid collisions with it? We started with the intuition that, let's say there's an abstract obstacle. What do I need to do for a mission critical system? I need to determine its position, classification, dimensions, so I can not only see where the obstacle is right now, but also predict where it's going to go in the future. There's a lot of prediction, behavioral prediction that happens in mission critical systems. However, this is complex and definitely requires the use of deep learning because we do not have good classical solutions for this. But just to avoid colliding with an obstacle, we just need to know that there is an obstacle. For a pessimistic system where we want to avoid all collisions at any cost, we want to be able to know where an obstacle exists. This turns out is simpler, and we can use geometric algorithms to do it, which are fully explainable for their behavior. They can be completely analyzed and therefore verified. Working on this intuition, we tried to formalize this analysis. Using a reach avoid control problem, we figured that if our reach problem is that we want to go from point A to point B, while our avoid condition is avoiding any collisions, though not optimal, we can create a planning where we are only considering the set of obstacles that exist without their individual classes. Of course, we do not want to consider every obstacle that exists in infinite distance from our system, but only obstacles which pose a risk of collision. So for that, we just use simple Newtonian mechanics to understand based on whatever information we have currently and pessimistic bounds for the information that we do not have. We can create existence regions for both the obstacle and our vehicle over a time frame and see if there's a potential for collision. For ground vehicles, height is also not an important factor beyond a certain cutoff. Above that, the exact height of the obstacle is immaterial to avoiding collisions as long as it is above a certain limit. That changes when we go to air vehicles because there the height of the obstacle, considering we can plan above or below the obstacle, also is a factor. Distance is an important consideration. Underestimation is a performance issue, but not a safety issue. Overestimation, however, is a grave safety issue. And so, but at the same time, we have to allow some level of error in the detection system. So we have a specific bound for what we use for the overestimation error. And I'll discuss later how we actually integrate this error allowance in our system. Finally, rather than detecting the complete bounds of the obstacle, we only create the requirement to detect a projection of the obstacle towards our system. In ground vehicles, this is a line in a 2D space, but in an air taxi, this will become a plane in a 3D space. So the next step is, do we have existing classical verifiable algorithms that can fulfill these requirements, or do we need to create our own? Thankfully, for LiDAR-based systems, there exists a prior work on depth clustering algorithm. What it does is, it considers the depth discontinuity of LiDAR returns. So if, my bad, let me enable my pointer. So if you consider the discontinuity, the modification of the return of this LiDAR beam because of the existence of this obstacle, it can be measured by these alpha angles that are between the LiDAR beam's return points and the obstacle and the ground. By thresholding these alpha angle changes to some prior value, the algorithm is able to differentiate between small bumps in the road to actual obstacles. This is very tightly coupled with existence of a ground plane, and I'll discuss later how it can be applied to air taxis. Why would we even want to consider these kind of algorithms? Where deep learning is primarily based on learned correlations between input data and the output expected, classical algorithms are based on causal logic between the input and the logic on what we want to do with it. Deep neural networks, however, have enabled capabilities and performance that classical algorithms cannot, where they are severely limited in some ways. On the other hand, deep neural networks go through only empirical high confidence validation, whereas for these classical algorithms, we can completely analyze and verify their behavior. The abstract nature of the features of a deep neural network limit how human comprehensible these features are. On the other hand, for classical algorithm, for example, in this depth clustering, everything is angles, distances, etc., right? Things that we humans can comprehend, which means that once we can comprehend these limitations or features, we can create effective policy support to limit these features. On the other hand, such policy support will be exceedingly difficult for incomprehensible features. What all of this combined together gives us is something we call a detectability model for classical obstacle detection algorithms. Consider this oversimplified example that there's a safety policy that says we must detect all obstacles of a minimum size y, some parameter y. The detection requirement is that we detect both the existence and the position of the obstacle. The model may be just a simple inequality that, okay, in this green region where the inequality is met, the model is valid. The values M and C could be dependent on sensor and algorithm parameters. This model may not be universal. There may be validity constraints. For example, LiDAR has severe limitations in unclear weather. But when these validity constraints are met and the model is well formed, we have a safety guarantee. We have a verifiable guarantee that obstacles are always detected when this inequality is met. So we actually, in our recently published work, we find that not only can we create such models for this algorithm, they might give weird bounds for the actual equations. However, this zigzag is simply because of the discrete nature of the LiDAR beams, which is not as useful, but we can create linear maximum bounds, which are very much usable. And I'll show later how we use that in our system. How would we use this detection algorithm in air taxis, considering how much it is bound to the detection of a ground plane? Well, consider this example where there is no obstacle, and this denotes the maximum range of the LiDAR. There is a certain pattern to the angles that are formed between the LiDAR return triangles. The existence of an obstacle modifies this pattern completely, and by measuring this pattern and bounding this change by a threshold limit, we can still apply this algorithm to air vehicles, and that's one of the planned future works that we have. Air, another very important factor is the weather effect. While it is also sometimes important on ground, in air taxi, this is definitely an important consideration for use of LiDAR. We adapt to that by using an attenuation coefficient of how much of the LiDAR beam energy attenuates when it's passing through its medium. It is based on detection of a visibility of the current air medium, and there are significant prior works on how this can be done on physical systems. Using the wavelength of the LiDAR beam, the LiDAR laser, and another parameter based on the visibility, we can figure out this attenuation coefficient. And using that attenuation coefficient, we can figure out the reduction in the effective range of the LiDAR sensor because of this attenuation. As a general rule of thumb for the wavelength of typical LiDAR sensors, this reduction can be up to 10x in haze and up to 100x in very dense fog. Finally, how do we use this system into this verifiable algorithm into the overall autonomous driving pipeline? Well, let's consider a mission layer system, which is, let's say, a complete end-to-end driving solution for autonomous ground vehicles. This can be a single neural network, as prior works have shown, or it can be a discrete graph of many different solutions, which do include deep learning-based solutions. This mission system is responsible for the mission of the system, which is navigating from point A to point B, while also doing a best effort job at maintaining safety, which is collision avoidance. If this mission system fails at maintaining safety, the mission of the system can no longer be guaranteed. We integrate our verified obstacle detection algorithm over it and introduce a fault detection and handling logic. And this combined is our safety layer. What this lets us do is create a safety monitoring envelope around the vehicle. Let's say an obstacle enters this monitoring envelope. Using the object detection in both mission and safety layer, we can create a carve out that this obstacle makes unsafe for the AV to travel into. When the envelope for mission generated by using the output of the mission system does not match the one generated by the output of the safety system, we override because the mission layer is working and planning off of faulty perception data. However, if there is no disagreement between the mission and safety system, then we let the mission system control the vehicle without causing any interruption. The verifiable limit that we get out of this is a maximum velocity of the vehicle, where we can always reliably detect the incoming obstacles within our envelope. So using the detection range of the LiDAR, which is the minimum of detectability limit that we get from the detectability model and obstacle policies, and the LiDAR range limit, which is the effective current LiDAR limit based on current weather conditions, we get the maximum possible detection range. From this detection range, we have to subtract any safety margins that we have introduced into the system to get the maximum distance that is the laxity we have for responding to a vehicle, to an obstacle. And if such a override is required, we brake to halt in response to this obstacle. And this considers, so the maximum safe velocity that we can maintain considers both the maximum deceleration of the vehicle and the computational latency of the safety layer system. This maximum deceleration is either a constant, a presumed worst case, but we can do better, and that is something I'll discuss later, a little bit later. So we evaluated this system.
Yeah, okay. I want to pause and answer one Kevin question he asked about the real time. It turns out that the LiDAR detection also gives us a range information. From there, we can calculate the highest risk, so the time to collision number. So from the distance, or even better, time to collision, we can prioritize the vision, say, look at this and tell me what it is. Now, why we want to know that? That actually is very useful for trajectory planning, especially you want to bypass a slow car. If you see a tractor, you know the maximum velocity of tractor, and you can plan whether or not, like on a country road, you can bypass it without hitting the ongoing traffic. But it's a Ferrari, probably going to think twice, because the maximum velocity of Ferrari is pretty high. So whether or not you have room to bypass it. Also, in the last ditch damage control, say somebody cuts in, just doing something crazy, the collision is unavoidable. Then you rather with a collision, you hit another car rather than hitting a bicycle, a person on a motorbike, because so therefore the synergy exists. The ability is to know which one pose the maximum risk in collision, allows us to prioritize where the machine learning should look first, just like what we are driving. In a very dense situation, you want to something, you just look at the nearby car, but not the one far away. So the list actually goes on, but just I want to cite one reason. A private student worked with us, and he showed that if we are able to prioritize where we should recognize things first, and then spend a bit more sort of computation power to look it closer, rather than sort of from the top left and then first come, first serve. It can make a world difference for as the real time for the machine learning output is concerned. And that was actually getting a best paper award from the Real-Time System Symposium. So this work, yes, it also enables the real-time processing. an image of vision, an image. I don't know whether or not that makes sense to you, Kevin.
I'll mention that again when we come to the appropriate slide where that is kind of motivated.
Okay, all right.
Yeah. Yes, thank you.
So we evaluated this by implementing it over where the mission layer is Baidu's Apollo 5.0, and we integrated the existing obstacle detection algorithm, creating our own fault detection, criticality determination, and override logic. This was implemented in a software in the loop simulator simulation setup, where LGSVL is the environment simulator and provides sensor data and the vehicle interface, and where Apollo integrated with our safety layer provides the autonomous driving control. This is very similar to the photorealistic setup that Hyunjin presented 2 months ago, but it only supports ground vehicles. So that's a great work that he's doing to also add such capabilities or such simulation setups for air vehicles. So we create a simple scenario, which is actually very, very prevalent in the real world fatal collisions, where some obstacle in front of the AV was, or in front of the autonomous ground vehicle was not detected. 3 things may happen. We may collide with this obstacle, we may stop before it, or we may safely pass it. If we collide with the obstacle, we have violated both the mission and safety requirements of the system. However, if we stop before it, we meet our safety obligation, which is avoiding any collisions, but we have had to abandon the mission. But if we can safely pass it, both the requirements are met. We ran the simulation with different initial velocity and different initial distances multiple times, noting what is the outcome for each case. 3 setups are evaluated for the autonomous ground vehicle control. First, we directly let Baidu's Apollo control the vehicle, which is the mission layer only. Second, for a synthetic best case for safety, we crash the mission system as soon as the simulation starts, which means the vehicle just starts braking as soon as the simulation starts. So this is the synthetic best case. Finally, the actual target of this evaluation is that we inject an obstacle existence detection fault into the output of the mission layer system, so that the safety layer, when it detects collision risk, tries to avoid that collision by braking. When the initial velocity of the autonomous ground vehicle is less than the Vmax safe that is calculated based on prior shown formulas, we see that whatever collisions could be avoided are always avoided. And that means the actual response of perception simplex is equal to the best response possible in this scenario. This figure shows the same simulation results, but in a different format. So this 2-dimensional pattern shows the initial velocity and initial distance. Each dot represents the worst outcome out of 10 repetitions for the same initial velocity and distance. If there's a green dot, that means we stopped safely. If there's a red cross, then there's collision. And the blue line shows where the Vmax safe was. Again, we notice that below that limit, the best case response and our actual response are identical. However, above that, there are collisions which are expected because the initial velocity of the vehicle is beyond the Vmax safe. We also plotted out the speed of the vehicle using both the mission and perception simplex system when there is no injected fault and there is no risk of collisions. We see that there is a lot of braking in the starting. This happens because at this time, the mission system has yet not acknowledged the existence of the obstacle, while the perception simplex safety layer has. And there's a inbuilt recovery mechanism where we reduce our speed, so the collision risk subsides, but then we try to increase it again, and as soon as we detect collision risk, again we reduce, till the time we go to a place where the mission system reliably detects the obstacle and there are no more faults. The other aberrations here happen when there is not enough overlap between the mission system and the perception simplex system safety layers, object detection range, or the object detection dimensions, and due to false positives. So how do we adapt this to air taxi? Well, consider that using the same logic, we get a maximum allowed distance of object detection. This object detection distance can be used in the same way for providing the fail-safe when an obstacle existence detection fault is determined. Unfortunately, for air taxis, stopping in place is definitely not a great override. If we require external support to get out of the current condition, this creates a lot of external dependence that is not really a good design. So we have met our safety goal and we have created this verifiable fail-safe system. But then how do we make it fail operational? And especially for air taxis, how do we reliably, or at least for the best effort, try to recover from this situation? So we do that by enabling synergistic interactions across our mission and safety layer. So one very big way in which mission layer can help the safety layer is providing additional override options. So when a fault is detected, we are able to ask the mission layer to do override options for us while still maintaining our fail-safe behavior. For example, by providing the, we can ask the mission layer to focus on where that fault exists and try to detect that obstacle. Or we can provide it whatever information we have with respect to the detection of that particular obstacle that the mission layer system cannot see, and use that limited information to plan a path around that obstacle. This is also where Professor Shah suggested integration with Professor Tariq's work come in, where these verifiable algorithms actually work pretty fast. They work at the rate of up to 100 hertz on embedded platforms. So these initial early detection of where obstacles exist can be provided to the mission layer to optimize the mission layer behavior. And that is the work that Professor Shah was mentioning in collaboration with Professor Tariq's group. So in the air taxi, this enables better fault responses where the fault notification to the mission layer can help us completely mitigate the fault, or we can at least try to plan, we can use the mission layer capability to plan around the obstacle. This is ongoing work. We are still working on this in both ground vehicles, and we try to adapt it now to air taxi. But now we are able to see a path to utilizing machine learning capabilities while maintaining our safety guarantees to improve the overall system. Final work that we are doing here is, we have talked about synergistic interactions between the mission and the safety system, but there is another level of synergy we can enable between different components of the system. So consider this case. We consider that our maximum deceleration is some constant or some pessimistic worst case. However, we have a control system that is aware of the current conditions and how this deceleration, what deceleration can be safely provided right now. So if we have dynamic confirmation between our worst case planning and the control component, we can continuously update what is possible today. But there's a clear limitation here. Well, we know the current deceleration, but how do we know how this is going to change over the path that we need to take to stop? This is a more common problem. Control systems today adapt to the changing environment, and Professor Naira's group has done some great work into these adaptive systems. However, these current adaptations are reactive to changes in the environment. By leveraging perception system, we can predict or basically detect when such changes are going to come up, and we can provide these upcoming environmental changes to the control system. As a very simple example, when we are approaching the ground, so the ground effect on the air taxi is going to increase, we can provide such information to the control system so it can proactively prepare for the adaptation to this change. And using these techniques, we want to minimize any kind of performance loss that happens because of our integration. Overall, the system is supposed to be a verifiable fail-safe and a best effort fail operational system. We have been, as I mentioned before, we have been using a solver in the loop simulation to validate this, but now we are trying to deploy our solution on a real vehicle, Polaris Gem E2, and verify that our solution works in real world scenarios also. We are also grateful to Professor Petros and Hyunjin Yoon for providing their photorealistic simulator for the same validation with air taxis. And we are looking forward to their integration of NASA General Urban Air Mobility model into their simulation setup and use that. These are all the people that have been involved with, directly or indirectly, with this work, and I'm thankful to each and every one of them. So as I mentioned before, we try to utilize mission layer capabilities. One such thing we can do is, when there exist capabilities that safety layer has no verifiable way of achieving, for example, traffic sign comprehension, if the mission layer system is good and has been verified to or empirically analyzed to be high confidence, and because the system is already vulnerable to these faults, we can integrate this information from the mission layer into the safety layer to add some reliable cues for the context of our current driving. The traffic signs is a great example here because, for example, based on speed limit, we can modify what is the collision risk calculation for unknown obstacles. And now Simon will describe his work, which actually makes these reliable queues possible. Simon, feel free to take control of the presentation.
All right, can everybody see the screen?
Yes.
All right, so hello everyone, my name is Simon, one of Professor Shah's students. I'm here to present one of my current project, which it focuses on benchmarking image recognition and robustness under diverse attack, such as adversarial attack and distribution shift, using the concept of visual attributes. So I like to first motivate our problem by examining the design of many state-of-the-art vision pipeline, which typically consists of two primary modules. So where the we have all the inputs that goes into a feature extraction module, which typically employs convolutional neural network, and then the output of that goes into a monolithic feature interpretation module, which typically consists of multi-layer perceptrons, which then generates the output. Oops, sorry. And so all of the feature interpretations are trained in these state-of-the-art pipeline. The feature interpretations are trained directly into the monolithic or multi-layer perceptron head using purely data-driven approach. Using this approach, the internal logic of the multi-layer perceptron head during training and inference remains as a black box to us humans. And that kind of limits the backtrace and analyzability for any mistakes or misclassifications made by the multi-layer perceptron head for any reasons. And aside from such a monolithic feature interpretation design, many existing deep learning vision data sets also only designate a very simple label for each of the class. And such simple label provides no additional descriptions of any additional attributes or features of the object aside from exactly what it is. And such data set essentially just expects the vision pipeline to simply just figure out what features corresponds to the object all on their own. With this design, we have sort of a limited knowledge on exactly what kind of features that the vision pipeline themselves have decided to associate with the object for to perform any recognition, which might produces an unbounded level of spurious or error correlations, just simply due to the fact that we don't know exactly what feature correlates to the object. And we can improve the situation by replacing the monolithic feature interpretation with a set of individual components, and each of which is responsible for detecting only one aspect of the object or one visual attribute of the object. And in fact, this is some of the concept of this idea is already explored and presented by Professor Bowley during the last seminar, where she employed an ensemble of networks, and each of which is responsible for only one attribute for the decomposition. And she also has explored using first-order logic, as well as some probabilistic graphical models such as Markov logic network to combine the output of all of these decomposition parts, and which forms the final output. And there also exists many other ways for decomposition and composition, such as employing a multi-task learning pipeline, where each task head, only each task head is responsible for one attribute, such as the picture presented right here. And we can also employ some additional composition approach, such as probabilistic circuits, such as sum product network, which can also have some theoretical benefits. And all of this goes to show that there's great benefit of trying to integrate the concept of visual attributes into improving the architecture design of the neural network, and thus improving the robustness of the recognition. And with the benefit of the decomposition, however, there also comes the drawback where since we pass one input into the vision pipeline, and all of the visual attributes exist all at once given any input, the model might gain unintentional reliance on unrelated cues instead of all the desired attributes. For example, if you were to train a vision pipeline to recognize a stop sign, the model might establish undesigned classification error correlation between the shape and the color of the sign, simply due to the fact that the octagon shape and the red color co-occurs in any given stop sign inputs. And we, in fact, demonstrate this level of error correlation in the decomposition pipeline, such as the multitask learning network, by performing a task targeted on one task while also observing its effect on all the other tasks. And we hypothesize that this error correlation exists not only in the multitask network, but also in many other pipelines, such as the ensemble networks, simply due to the fact that the visual attribute simply co-occurs with any given input. And I like to outline the work of our VISAT dataset and benchmarking suite by first discussing our approach in creating and formulating the visual attributes on a large-scale traffic scan dataset. And we also created a rapid visual attribute labeling software for us to efficiently create all the visual attributes for a very large-scale dataset. And additionally, we introduced a set of robustness benchmarks, which focuses on two major types of attack. One is the instance-wise attack, adversarial attack. And in this benchmark, we employ a popular projected gradient descent attack algorithm. And we also explore dataset-wise attack method, which is known as distribution shift. And we have explored two methods, two distribution shift methods. One is called color quantization, which I will get into details in the later corresponding slides. And then we also employed the ImageNet-C data corruptions and natural variation techniques to basically perform the distribution shift on the testing set. And essentially, our robustness benchmark suite will hopefully serve as an evaluation platform for gauging the robustness of all the decomposition components and designs. And last but not least, I will also like to discuss the potential applications on the urban air mobility and the eVTOL use cases of our VISAT dataset and benchmark suite. And so in our study, we kind of specifically focus on the context of traffic sign recognition. And in this case, we have devised 4 types of visual attributes, which are color, shape, symbol, and text, that kind of serve as a fundamental elements of features that kind of like defines all the typical traffic signs. And for the color attributes, we try to capture major background foreground colors, such as, for example, for picture A, we will label the color attribute of it as color red, white. And for the shape attribute, we directly encode the shape of a sign into the attribute. And for the symbol attribute, we try to describe all of the symbols on the sign by words in their geometrical order. And for the text attributes, we simply encode the text of the sign in the attribute if applicable. But sometimes in the cases where due to the limitation of the data set, where signs of the same type but with different texts are labeled in under the same class, we then try to capture the meaning of the text by giving a general designation, such as here we labeled picture D as text alphanumeric. And we also created a software for us to rapidly label the visual attributes given a very large scale set of classes. And the software has 3 different primary areas: the view, labeling, and application control divisions, which will help the human laborer to observe and formulate the visual attributes, as well as performing the rapid labeling of those visual attributes onto the data set. And we also try to make the software fully customizable to accommodate various screen sizes, as well as, more importantly, any type of user-defined attributes in the labeling control division. And this essentially makes our labeling software dataset agnostic, which means that we can use this software to facilitate creation of visual attributes for any dataset, so long as those visual attributes can be conceptualized and formulated by humans. And now we get into our robustness benchmark, and here we specifically talk about the adversarial tag employing the projected gradient descent algorithm. And for the projected gradient descent algorithm, it's worth to point it out that the attacking method is model specific, meaning that all of the generated attacks targets one specific model, and the algorithm basically is generated based on the model parameters, and it essentially maximizes the loss of the model by manipulating the input, however, within a given certain bounds. And the resulting attacks has limited alterations compared to the original inputs. As we can see here in the picture, we can notice some alterations, but not unbounded alterations. And they are actually very effective against any of the targeted models. And here we perform our adversarial attack, generated attacks on two major popular vision backbones, such as the Resonant 152 and the vision transformer VIT B32. And we specifically perform our attack on their multitask learning version, trained using our label created visual attributes. We generated 8 different attacks, and each of which corresponds to the 4 task heads that each of the network has, which also corresponds to 4 of the visual attributes that we have, and which we perform the same thing for both of the networks, which give us 8 attacks in total. And we can see here that when we apply for example, Resonant 152 attack on its color head, and obviously the color head will have a large drop. However, if we apply that same attack on other task heads such as shape, symbol, and text, we also observed significant drops, which shows that there's error correlation among the 4 tasks. And it's also very interesting to note that the VITB32 attacks are effective against also effective against the Resonant 152. However, the Resonant 152 attack is not so robust against VITB32 models. And we move on to investigate the robustness of the model under distribution shift. In this case, specifically the ImageNet-C corruption and variation techniques. And for this sort of attack, the attacks are model agnostic, meaning that the generated attacks do not depend on any model details, and in fact can thus be applied to any models. And the ImageNet-C technique consists of 19 individual data corruption and variation techniques as shown to the right, and each of which has 5 severity levels. And there are 4 major variation types grouped together, such as the noise, blur, weather, and digital. And we perform all the 19 times 5 equals 95 total corruptions on the Resonant 152 and VITB32 multitask learning network models. And then we can see that there are varying levels of effectiveness of the attacks depending on their types. And we can also interestingly observe that again, that it seems like the color and the shape attribute task heads are again sharing correlation in their dropping accuracy, where when color has significant drop, so goes the shape as well. And we can also interestingly observe that attack types such as blurring attack is not so effective against our model. We suspect that it's because some of the traffic signs in our data sets are already far away, and then when they're fed into the network, they're already kind of having the blur effects, which means that the blurring attack themselves are ineffective to be served as distribution shift. We perform the same experiments on the VIT B32 vision transformer model, And we observe similar trend, except that the overall dropping accuracy is lower, indicating that the VITB32 model is overall more robust against distribution shifts compared to Resident 152. And we perform a final experiment, which is a special types of distribution shift known as a color quantization, where we try to quantize or cluster elements of colors for each of the signs, allowing us to modify essentially their color palette. And this attack, in fact, is very attribute specific, since the generated attack specifically targets the color attributes with minimal to no impact on any other attributes. As we can see in the picture here, all of the symbol text and the shape of the signs are remain unaltered, while the colors are completely flipped. And with this attack, we apply the attack on the same of the two models that we have explored so far. And interestingly, we see similar trend where we are expected to see significant drops in colors, since that's the attacked task. However, if there exists little to no error correlations among the 4 tasks, we would expect to see minimal to no dropping accuracies for other tasks such as shapes, symbol, and text. However, that's not the case here, which again indicate that there's exists error correlations among tasks, especially between color and shape. And so in this study, we have performed a very comprehensive study on the model robustness using the concept of visual attributes and in the context of traffic sign recognition. However, the concept of the visual attributes itself is universal for pretty much any visual recognition tasks. And in fact, the visual attributes can be conceptualized and formulated for a lot of the tasks in the use case of urban air mobility and eVTOL, such as ground area recognition, where we, for example, maybe it's necessary for us to figure out what kind of area or neighborhood we're in. When we look at the picture on the right, the first picture shows a neighborhood, and the second one shows a factory, and third one shows a dense city. And obviously, they all have different visual attributes and cues. We can then try to formulate them and then use our tool chains and everything to create the visual attributes for these data sets, and hopefully allow us to have a more robust recognition on these tasks. And additionally, our study on the traffic sign recognition can also be helpful in the case where it is possible for certain eVTOLs to try to perform urban area insertion, such as trying to land on any parking lots, uncrowded areas. And once the eVTOL has landed, and if it has any driving capabilities, it still has to follow the local traffic laws, and thus requiring it to recognize any signs nearby. And as we have mentioned before, our rapid visual attribute labeling software is dataset agnostic, and therefore can be used for many other vision datasets. And obviously, our robustness benchmarking pipeline is also will remain useful in this use case, and in fact can be adapted to evaluate models on focusing on the urban area use cases, and hopefully serve as a robustness evaluation platform for any future decomposition pipeline designs. And our VISAT benchmark and the dataset are submitted to the New York's conference, and is already available to the public via this link. And in the near future, we actually plan to explore specific decomposition and composition pipeline designs by employing the multitask learning network, as well as some versions of probabilistic circuits. And then we can use our benchmark and dataset for performing evaluations. And I guess I'd like to summarize our entire presentation by performing a short summary on our system model, where we try to achieve a safe and air plus ground vehicle without, I guess, use of specific landing pads. And in our overall architecture, there are 3 key components. where we have verifiable safe collision avoidance using physics model that supervises the machine learning vision. And then we also have tried to perform robust and I guess statistically safe or reliable traffic sign recognition against a diverse set of attacks. And we aim to integrate safety-driven safe perception, such as the safe perception components, such as the perception simplex Ayoosh have discussed, as well as the existing safe control modules, such as the L1 simplex, and all of those components form our synergistic simplex architecture. And we hope our approach, we aim to extend our current research on the context of urban air mobility and eVTOL, and hopefully we can improve the overall safety of the system. Yeah, if you have anything to add, Professor Xia, you can discuss right now, but otherwise, I think that's the entirety of our presentation. Thank you very much.
Thank you, Simon. Luis, so anything you have to add or questions?
I just want to add a certification perspective. As you see, we said that currently we see that the vision part, like I say, the sign recognition, remain statistical. That means we cannot, like the obstacle avoidance, we can do it deterministically. So, but why we said our architecture is still safe? The reason is once we achieve verifiable obstacle detection and avoidance, even the whole recognition, say, I don't see the stop sign, just fail to recognize it, or the entire machine crashes, then we might get a ticket of passing the stop sign without stopping, but not hitting another vehicle or person. Okay, so that is the important distinction. That means once we are certifiably safe obstacle avoidance, detection avoidance, then using statistic approach on traffic recognition is okay. We may get a ticket, but we won't run into anything.
Do you mind if I ask a simple question about the in your mission layer? Are you keeping or generating track files on all the obstacles so that you know their relative velocities, where they're headed, how fast they're going? So basically, you know, you're doing track file management in the mission layer. Is that correct?
Yes. So Baidu's Apollo does support that.
Okay. Let's see. I thought this was very interesting, particularly the error correlation. Simon's work there, that this last part that was briefed, I think that's of critical importance. So, very good.
Yes. Thank you, Kevin, because that's a generic witness in the current vision AI architecture. Because that really makes what we used to do in fault tolerance impossible, because we always want to make sure independent fail mode between different redundant components. That correlation essentially destroys the very foundation of certifying a robust sort of redundant systems or sensor fusion. So this really points to we need to innovate and develop a new generation of machine vision architecture where each feature's fail mode or classification error will be uncorrelated. So therefore mathematics can be applied. And in fact, a lot of existing mathematics can apply to derive the overall system reliability. With such correlation exists, and also in a soft manner, that means we cannot really calculate accurately. It really destroys the reliable, our goal of robust vision. So we are confident. We already seeing ways forward. Hopefully just after a few while, we'll develop a new generation of machine learning vision architecture which are virtually free from this error correlation problem. That's
Yeah.
our goal.
I think let's see, I have limited experience with this, but in Boeing, we use different sensor modalities and then try to overlap them to help reduce this correlation problem. Yeah.
Yes, this correlation is a big challenge, but
Yeah.
I think we'll try to solve it, and we are quite confident.
Yeah, good. Yeah, that's all for me. Thank you. Excellent briefing.
Thank you, Kevin, for joining, and thank you for the questions. Let's see if we have more questions from the audience. If not, we'll close and provide the recording and the slides for everyone on the extended team. Today, we didn't have anybody from NASA, which is surprising. Usually they join, but I guess Monday holiday has made it extended long weekend for them. That's my feeling. NASA goes on extended long weekends, right? Monday holiday hurts our Friday meeting. But they watch, they send questions later. This is good.
I think a lot of the government labs take off every other Friday, right?
Really?
Yeah, I think they started doing, I think a lot of the labs are doing that.
Louis is in Hong Kong. It's 1 a.m. for him, Kevin. Imagine. He's sitting 1 a.m. for us.
Kevin, I heard that you're going to retire soon. We'll miss you.
Oh, yeah. Well,
We hope that you can hang in here helping us.
Can't stay forever.
So he will help us, right? He won't retire from our project. He will retire from Boeing at most.
Hopefully.
Hopefully he does not.
Okay, so Kevin, we all have great respect for you, because you know how both on the research side, the government side, and of course the Boeing industry side. So what is your guidance? You saw we have maybe something we should do more, something we should do less, or something we have some blind spot we should pay attention to?
No, I'll just say that the topics of certification and creating certificates that we can use to validate these training components that are embedded within our control architectures. I think this is still a open problem. It's very interesting to see the different approaches being done. I sent an email to Irene yesterday. There's a number of ULIs. There's 3 of them that are all different teams doing different things. And so I've only been engaged with this one. It'll be interesting to see if there's maybe some cross-pollination between these teams. I would just say that might be beneficial. So next week I'll be going to Stanford for this meeting that they've got next Thursday. So I'll be able to see what they're doing in this regard here. But I'll just say that in some of the work that we're doing here at Boeing, where we're using machine learning components in our control architectures, there's excellent performance, but it's still, the safety guarantees and I'll say certification aspects of this software is still in question. So I think the whole community, we need to put this out there, get the whole community to agree, and get our customers to agree that these approaches are what we want to do.
Yeah, that is something you can help us a lot.
Yeah.
I think Dr. Yu said, actually, we talked to him a little some time ago. He said that at least his group is planning to adopt the L1 simplex, the four-horn architecture. I don't know how far it's gone. Probably we should contact them. So because the L1 simplex allowed arbitrary control software fail and some limit mechanical fail, and yet we can verifiably guarantee the stability and safety. So that's the control software. Now we heard that the approach by Ayoosh, he helped to extend the simplex architecture to vision that's today. So the spirit of simplex architecture is actually very, very simple. You want a simple and verifiable model, create an envelope or sandbox, which is provably safe or certifiably safe. And then let the machine learning within the confine of this safety or stability envelope and improve the performance. So therefore, we can get the performance, but without paying the price of occasional catastrophic fail. So we can think about it as we get a constitutional right, constitution, which is a very simple right. And then the state government or city government can make their state law, but cannot be unconstitutional. So you can think about that. So people ask me, will this approach work in larger system? My joke is, if this schema is good enough for United States of America, probably it's good enough for software. That's my joke.
Very good.
So maybe we can, what I'm really trying to say is, maybe this team led by Naira can go through a number of use cases, building interest use case, say desensitize the use case, such that if we can solve this unclassified, unproprietary use case, then Boeing can make use of the technology to solve proprietary or classified cases. I work with industry. That approach has work. Yes.
So,
can we do that?
We're I'll just say that, Boeing is on target to field an air taxi, have it certified for the year 2028. But I think that the initial offering of this service will not have any AI embedded in the architecture, and that these components will then get added. But I think, we in the presentation today, and we talked about not having landing pads and things like the flying car side of it. But I think inserting this technology and getting the FAA to agree that these certification artifacts that have been produced warrant certification of the vehicle and incorporation into the architecture. There's still a gap between what the FAA requires and what we're doing, I think, at this level. So there's still work to be done. I think we're going to need, kind of like what you said, if I took a note there to talk to some of the Boeing folks about use cases, getting it would be nice to have the WISC folks involved, in this as well, because it would be good for them to see firsthand what this team is doing.
But they didn't join our advisory board. We need them. So I sent even an email to another WISC guy. He said he will try to arrange it for us. We can't get them on the advisory board. We have a challenge with it.
And probably Kevin can help. Sometimes you're an internal advocate. It changes the dynamic.
And what we need the ULI to be extended to 5 years. The other ULI from Illinois got an extension for 2 years up to 5 years. I think maybe you need to tell Irene and some NASA leadership that there is good work happening here, but it needs longer runway. We are already 1 year and more past the start. And if we get 2 extra years, we can do all this, because it's a big scope, ambitious scope, and yet it's very much down to earth. We all have this track record of flying testing, so we can bring it to.
I think the best argument for Irene to extend it is merit-based extension. From NASA perspective, we are currently in the stage of basic research, and which is true. At some point, if we can address that, for example, Boeing's need to build towards building this flying tax, then which is the best cases to get extension. And I did get some extension in the past, Essentially, so stage 2 is to make it work in collaboration with a leading industry partner. So for at this point, with Kevin's help, and we kind of start to integrate and start to solving the Boeing use cases. I think that is the best argument for a mission agency, not necessarily for NSF. Yeah, but for mission agency, they see the transition towards practice is the best argument for extension. Now, I want to say a word about certification. The reason is, I developed this real-time scheduling thing, and now it was, I would say, approved by FAA, and in fact, the only thing approved by FAA for level 8 control. So I went through the certification process, and through that process, I know Michael DeVore. He's the chief software certification officer. So we did talk about this simplex architecture. The importance, the common misunderstanding by the certifying community is the following. You are no way, you cannot have explainable and analyzable and verifiable behavior for AI. You are too far from that. Don't even talk to me for certification. A lot of people I said, you are absolutely right, but we still can't certify it. Why? If the certificate safety, we are not certifying the AI. We are certifying the AI will be boxed in by a verifiable classical algorithm. Let's say for collision avoidance and detection one, you certify what Ayoosh just showed you. It's a classical algorithm. The complexity is well within the certification procedures. In fact, it's a lot simpler than, say, docking the space station. So what I'm really trying to say is, what we are really is certifying the safety bound by physics models. Then in the AI, just doing the optimization. So we can have optimization fail, just like in Boeing aircraft. We might have mission layer fail, but it cannot jeopardize the safety critical layer, right? We even, we don't certify the mission layer as rigorous as the safety level A. In fact, you cannot do it. I mean, nobody can fully certify the mission control. It's too complex. Not even talking about AI, just talking existing software. So therefore, that the certifying procedure says that is that no fails in the mission system can ever jeopardize the safety layer, the level A. So what we are really doing is very much following the convention of aircraft certification. Our level A is the physics model constrained safety. So that means the AI has to play within the confine of the envelope of the safety, just like what we used to do. Now, if people start seeing that, we are not asking FAA suddenly change their certification procedure. In fact, we are consistent with them. Just need to look at things a little bit differently. Then the certification will become likely. AI is used to enhance, or say, the classical thing can fly the vehicle and certify it. We just want the AI to do some fine-tuning, so to speak. To think about AI as a mission system. So we can follow the conventional procedure to certify what we are doing.
So I agree with what you said there. I think the community at large is converging on engineering the safety layer to protect the system from, any issues associated with the AI components that are within there. So I think we're seeing convergence in these architectures. This would allow, I'll just say, people to develop components that can fit in, and then we use the safety layer to guarantee and protect the system. Then the question
Exactly.
Yeah.
Exactly. Just like a mission fail is okay.
Yeah.
Well, as long as we certify that the faults, all possible faults in the mission system cannot jeopardize the level A operation, and that's it. So certification is within our reach. What we are missing is people like you. A lot of people say, certify AI system? No way, too many states, there are millions of variables. You know, the model checking will run to forever. I say, yes, but it doesn't matter.
No. All right.
Yeah,
I'm gonna
we need your
to,
help. We need your help
yeah.
to get this program moving and get something real.
Good. All right, I'm going to sign out.
Okay,
Thank you, Kevin. Thank you for joining.
Oh, yeah.
See you next time.
You bet.
Okay, bye-bye.
Yeah. More questions from anybody? I mean, if there are no more questions, let's make sure we stop the recording and download the video. If there are no more questions. It seems there are no more questions and we are well past the hour. Louis, thank you very much for staying up this late in Hong Kong.
Oh, thank you.
Right.
Thank you for
it's an
creating
honor
this
for
opportunity.
me. Right? Thank you, and for these engaging discussions. You can go to sleep. We'll make sure we safely stop the recording and download it.